So why we need tensors? You remember at the beginning of my talk, when I presented different point groups, I said that most of the crystals are very symmetric or not symmetric? Not symmetric. Symmetry is quite low, right? So, and usually, for example, I mean, some of you are physicists and you know what are tensors and so on, but some of you didn't have tensors in university. For example, chemists, when I did my chemistry studies, I didn't have any tensors. And when you learn that, for example, if you take a conductivity, right, you have electric field and you get a current. Okay, so there is a conductivity. And you learn that this is a vector, and this is a vector. So current density is a vector, field is a vector, and this is a constant, right? So this is like normal way seeing conductivity or resistivity and so on. Yeah, but this formula is valid only for isotropic materials. So it means very, very symmetric. For example, cubic materials. But you don't have a lot of cubic materials. Most of them are not like this. And this formula is not valid. Okay? So why we need tensors? What we describe with tensors? It's a mathematical approach. How to describe the properties of not well symmetric, non-isotropic, anisotropic material. That's why we need tensors. Okay? So the aim is that, okay, I apply the field, for example, along axis 1 or x. Okay? So if my material is isotropic, my current will be along the same axis, right? Because it's a vector, and we are parallel or anti-parallel, right? But it cannot change the direction, current. Current will be always parallel or anti-parallel to the field, right? But it's valid only for isotropic materials. For anisotropic materials, if you apply the field along direction 1, you may get current also along direction 2 or 3. And how you describe this equation? You cannot do it because you have vector, vector, and constant in between. So if you understand how works tensors, then you can describe any material. Anisotropic or isotropic, you can describe everything. Okay? So it's very important to know tensors. So what is, for example, we have different rank tensors. Okay? So we have zero order or zero rank tensor. It is a scalar. So everyone knows what is a scalar. So this is okay. Then we have first order tensors, first rank tensors. It's a vector. Okay, so vector, we have how many components who describes vector? It's 3. Okay, x, y, and z. We all agree that the vector, there is no sense of definition of vector if we don't have a coordinate system. We all agree. We need a coordinate system which is usually orthogonal, right-hand orthogonal system, and we describe vector in this orthogonal system. And we have x, y, z, so 3 components, 3 constants, which describes your vector in this coordinate system. So it's a very basic thing, let's say, till now. Okay? But if we change coordinate system, then we need to change the description of a vector. Okay? Okay, so second order tensor actually helps you to describe the relationship between vector and vector. So vector is the first order. So for example, current is a vector. So it's a first order tensor. Field is also first order tensor. Okay? So to describe a relationship between these two vectors, first order tensors, we need a second order tensor to describe the relationship between order 1 and 1. Okay? To describe a relationship between vector and scalar, we need a vector. Okay, order 1. Between two scalars, 0, 0, we need 0. And then to describe a relationship between, for example, tensor order 2, for example, like stress, it's a tensor order 2. Okay? And, for example, polarization, which is vector, it's order 1, we will need a tensor of order 3. So it's like sum. Order 2, 1, you need in the middle 3, and so on. 2 and 2, you get 4 in the middle. But don't worry if you don't understand at this point. You will see many, many examples after. Okay, so what does it mean? Okay, so we come back to the, so let's say, okay, this is a vector, this is a vector. So this one is a tensor of order 2. So it's not a constant, not a one constant, but we have 9 constants. Okay? So in principle, what does it mean? So example here is given between electric field and polarization through polarizability constant, okay, which is also tensor order 2, because this is a vector, so this is a tensor of order 2. So for example, polarization along axis 1, okay, here, okay, can be induced by the field along axis 1, along axis 2, and 3. And the value of this polarization will depend on the constant. So these constants, there are 3 different constants. Okay? So each constant describes how the field along the direction 1 will induce polarization along direction 1. How the field oriented along direction 2 will induce polarization along 1. The field along direction 3 induce polarization along 1 according to this constant. So we use each constant, so we have 9 constants, to describe how each direction of a field induces polarization in different directions. So you get, so these 9 coefficients we arrange in sort of matrix, but it's not a matrix, it's a tensor. Okay? So this is a tensor. So when we have these 9 constants, we can say, if we know the value of these constants, we can say, for example, if I say, okay, my material has like this, and I know these constants, say, okay, I apply the field along direction 2, along y. Then I can say immediately what is going to be my polarization along 1, along 2, and 3. Okay, so I can say how it will be in an isotropic material. In isotropic material, it will be the constants all are equal. So then it's, and it's also, we are also. So this is a basic definition why we need tensor. Okay, so if we go to the first, which relates a scalar and a vector. Okay, an example is pyroelectricity. Okay. You induce polarization with temperature. Temperature is a scalar, gradient, which is vector. Okay. Caloric effect, so it's just reverse of similar to pyroelectricity. Then polarization, heat of polarization, and so on. This is how we find out. Tensor, these 9 coefficients, they describe relationship between 2 vectors. Permittivity or dielectric, refraction index, conductivity, thermal conductivity, thermal expansion, polarizability, thermal, and so on. Deformation and temperature. Order tensor. Okay. Always, you have two values, you have a force. So you count the sum of. Zero order and second order, you need the second one in the middle. If it's first, you need two. So it's just a question how many coefficients you need to relate with how many coefficients. Okay, if you relate second order, which has 9 coefficients, with the first order, there's 3 coefficients defining, so you need 9 times 3, 27 coefficients. Okay? So if you relate, for example, deformation to the stress, deformation is second order tensor, 9 coefficients, stress is second order tensor, 9 coefficients. So it relates through elasticity, and you have 81 coefficient. Okay, I don't see you very optimistic. Yeah, it seems to be complicated. Don't worry, many of. Okay. Yeah. Okay. So when just example, but we will go through it. About the symmetry, okay? Symmetry of what kind of symmetry we have, and then you get different coefficients, some we are 0, some we are equal, and so on. But okay. So, yes, I just showed before with the symmetry. We use rotational matrix. Okay, rotational matrix. Okay, you rotate the coordinates, and you calculate these 9 coefficients, which relates the cosines between different axes, old axis and new axis. Example just given, so you can check how to do it. You write 9 numbers. Okay, so then you have 0 order tensor scalar. You don't need to rotate anything because it's not dependent on your coordinate system and coordinates, so it's not a vector. In the case of a vector, you just apply once rotational matrix as you usually do. You rotate your vector, you redefine. So you saw an example of a second order. So you relate I to K and G to L. So you apply twice your rotational matrix, okay, for each coefficient. If you have third order tensor, then you have IGK. So you have like 3 times coordinate, and on the other side also 3. So you have 3 times rotational matrix. And in the case of a 4th rank tensor, you transform according to the 4. So you relate each, for example, in case I to M, G to N, K to O, and L to P. And you write 4 times this rotational matrix. And then you imagine how long it would be to writing each by each, and so on. So it's quite complicated. Okay. So luckily we have a software. So the question, what is the difference between transformation matrix, rotational matrix, and the tensor? For example, second order, like 9 coefficients and 9 coefficients. Okay. So when the tensors might be symmetric and antisymmetric. When we say the tensor symmetric, it means the diagonal, it can be any number, okay? But when across the diagonal, for example, the 1, 2 and 2, 1 components are equal, okay? 1, 3 is equal 3, 1. So it means that IG we replace with GI, okay? Is equal to 2, 1. 1, 3 is equal to 3, 1. 2, 3 is equal to 3, 2, okay? So this is symmetric. And of course, in the diagonal, it's 1, 1 equal to 1, 1, and 2, 2 is equal to 2. And so on. So the diagonal is free, but then when you have symmetry across the diagonal. So antisymmetric, we have the component IG is equal minus. So it means that 1, 2 is equal minus 2, 1, and so on. That's why the diagonal has to be 0, because if 1, 1 is equal to minus 1, 1, it has to be 0, because there is no sense. Okay, so luckily, most of the physical properties presented by second order tensors are symmetric. So it means we don't have 9 coefficients, but we have only 6 coefficients which are different, okay, not 9. Okay, okay, so we have 9 coefficients, but usually it's only 6. So we need to find, when we calculate, for example, we transform, we need to just find 6. So it's already shorter work. Okay, so we have tensors, the tensors. Okay, I want you to practice a little bit. Okay, so I want you to find an effect of cubic symmetry on a second rank tensor. Okay, and so we take a general tensor. So we have this rotational matrix, which is 1, 0, 0, 0, 0, 1, and 0, minus 1, 0. Okay. Your x, y, and z. Oh, sorry, it's easier to write x1, x2, and x3. You'll get to what? Okay, and then you try to transform your components. So it will get to x1, x3, and minus x2. So it means 1 goes to 1, 2 to 3, and 3 to minus 2. Okay. So it means it will get alpha 1, 1, alpha 1, 3, alpha minus 1, 2. Right? Alpha, oh, I said it's symmetric, okay? So it will be faster a little bit. So it's 1, 2, is 1, 3, and 2, 3. Okay, because it's symmetric. Okay, so it's only 6 to find. Okay, so this one it will be 1, 3. When we have alpha 3, 3, then alpha 3, 2 minus, and then alpha minus 1, 2 probably, and alpha 2, not 2, 3, and 2 and minus, and then we have alpha 2, 2. Yeah. Okay. So we agree that in a cubic system, so we have this fourfold axis along a axis, okay, or x-axis. So it's a symmetry element. So what we said that symmetry element is doing, if you rotate, you apply symmetry element, you cannot say that I did something. It has to be exactly the same thing. So it means that this description has to be equal to this one. Okay? Because I apply a symmetry element. So we have to be equal. So what does it mean? Okay, alpha 1, 1 is equal to alpha 1, 1. Okay? But then if you look, alpha 2, 2 is equal to alpha 3, 3. And then if you look, alpha 3, 3 is equal to alpha 2, 2. So it's the same. Then alpha 1, 2 is equal to alpha 1, 3. Okay? If I look, alpha 1, 3 over there is equal here minus alpha 1, 2. I don't know if everyone is following, but I'm going fast. Okay, so alpha 1, 2 here is equal to alpha 1, 3. Okay, if I look now to alpha 1, 3 here, equal minus alpha 1, 2. So I said, okay, alpha 1, 2 is equal to alpha 1, 3, but alpha 1, 3 is equal to minus alpha 1, 2. So it means, yeah, that alpha 1, 2 is equal to minus alpha 1, 2. So it has to be 0. Okay, and then I will look, because I already eliminated all these guys. So alpha 2, 3 is equal minus alpha 3, 2. So it's equal to 0 also. So applying this symmetry, the conclusion we get, only the fourfold axis along x-axis, we get that we have alpha 1, 1, then alpha 2, 2, alpha 2, 2, because we are equal. So I just will write one coefficient instead of 2. And here we have zeros. 0, oh, I wrote in a little bit disaster. Okay? So it means if material of a second order tensor, if material has fourfold axis, you already have one coefficient different than two, that is along x-axis, okay, a-axis. So now we have also threefold axis along 1, 1, 1, okay, which has this type of rotational matrix. So now I don't need to apply on 0, okay. My tensor is only alpha 1, 1, alpha 2, 2, and alpha 2, 2, okay, and all remaining is 0. So my rotational matrix is 0, 1, 0, 0, 0, 1, and 1, 0, 0. If I apply on x1, x2, x3, we will get x2, x3, and x1. Yeah, it goes to x2, x3, x1. So it means that 1 transforms to 2, 2 transforms to 3, and 3 transforms to 1. So it means that my new tensor, it will be alpha 2, 2, alpha 3, 3, and alpha 1, 1. Okay. As I apply the symmetry element, we have to be equal in between, again. So it means that alpha 1, 1 is equal alpha 2, 2, alpha 2, 2 is equal alpha 3, okay, from this. So it means that all the coefficients, the answer is that is alpha 1, 1, alpha 1, 1, and alpha 1, 1. Okay. So we see that the second order tensor, whatever is the property behind conductivity, resistivity, dielectric constant, refractive index, whatever it is, if it's a cubic system, which has fourfold axis and threefold axis, it has only one diagonal coefficient. Okay, so it's like isotropic material, cubic. So we have an example on the slides, how it transforms and so on. Yeah. So we see that it's totally symmetric system, cubic, for the second order tensors. So if we summarize, so we can do the same for each symmetry, for each point group. We can calculate, and someone did the job before us. So we don't need to recalculate, okay? But I wanted just to show you from where it comes and how it works, okay? How we transform these tensors. So in the cubic systems, for the second order tensor, second rank tensor, for cubic systems, all the three coefficients are the same, alpha 1, 2, and 3. They are the same, so it's like isotropic system. For uniaxial crystals, what we call tetragonal, hexagonal, and trigonal, okay, we have two independent coefficients. Okay, so we have unique axis along z-axis, okay, which is a fourfold, sixfold, or threefold axis along z. And we have a different coefficient along only this axis. And in the plane is isotropic. So it means it's equal. Alpha 1, 1 is equal alpha 2, 2. Okay. In orthorhombic system, so we have three perpendicular second order axis or mirrors. Okay. We have three different coefficients, okay, and all are zero. So if we go to monoclinic system, then we will get that we have four different coefficients. And in triclinic system, because we have symmetry 1 or inversion, okay, and inversion is doing your tensor symmetric around your diagonal, okay, you have 6 coefficients. Okay. So actually now, if you want to say, okay, I have orthorhombic material, what is my resistivity or conductivity? I hope that you will think that you have 3 different conductivities or resistivities, and it depends along which direction you are. There is no one value, there is 3 values. Okay, so when there is a way to represent different order of tensors, so for the scalar is easy, everywhere is homogeneous like a sphere, then you have a vector, then for second order tensors we use a quadric, like ellipsoid, than a cubic and quartic. So we have different geometrical representations. Okay, so we talked about the properties, but also some forces we will describe using tensors. Like, for example, a stress tensor. Stress tensor is a second order tensor and actually describes, because, I mean, it's very easy to describe a system which is just pushing along one direction, a force, okay? But your force might be like, for example, hydrostatic pressure, compressing from all the sides. It's not so easy to describe this force by using one simple vector, okay? But you can describe by using a tensor. So if you use a general description, like mechanical force, you use a second order tensor. Like this, you can describe any force, mechanical force, which is subjected on your body. Okay. So in definition, it's quite easy. So we have the first number on a stress. So I use sigma for the stress here. Is 1, so it's showing the direction of a force, and 3 on which plane is applied. Okay. So 3, it means it's the plane perpendicular to z. The force is applied along direction 1 on the plane which is perpendicular to z. Okay. 2, 3, it means it's on the plane 3 along direction 2. And 3, 3, it means applied on the plane 3 along direction z. And it's the same for others. Okay. So we have 9 coefficients, and we describe by the second order. Okay. So the basic stresses like compressive, tensile, we will describe just with diagonal. Okay, sigma 1, 2, and 3, so it's proper values of the vectors. And then, for example, uniaxial stress, which is just applying on one direction. So, for example, this is uniaxial stress along x. If you apply uniaxial stress along y, you just put here a value and everything will be 0. In the case of biaxial stress, you will apply along, you will have, for example, sigma 1 and sigma 2. If it's homogeneous biaxial stress, these two values will be equal. So it's biaxial stress in the plane xy. Okay. If you have biaxial stress in yz, you just will have values here, 2 and remaining 0. Okay. Hydrostatic pressure, because it's compressive, so we put a minus in front, and all the diagonal is equal because you're compressing on the 3 sides in the same way. Okay. And then shear stresses, we describe, you can put 2 values which are equal on the diagonal but with opposite side. So this is the shear stresses on xy plane, or you can put the values xy. It will be equal description. Okay, xy and yx. Okay, so it's the shear stresses. Oh, I'm sorry for image. So yeah, we have compressional, tensional, shear stress is just some illustrations how it would look, or we have hydrostatic pressure on all the sides. Okay, so the strain tensor, the deformation of your body, the same as a stress, you describe a second order tensor. Okay. Just the difference that, I mean, in deformation, what we talk about in deformation, we will look at the elongation of the axis. So for example, when you write, this is E, but epsilon, for example, 1, 1 component, so it will be elongation along direction 1 of the initial parameter of your length along x, for example. Okay. So when we have, so this is an example, yeah? So this is like your strain along, or 1, 1, okay? Your deformation along 1 is equal, according to this deformation coefficient 1, 1, delta x 1. So it means that this length, delta x1, was elongated by delta u1. So the coefficient e11, or deformation 1, 1, it means elongation along direction 1 of initial dimension of along 1. Okay? So just how much your axis x is elongated with respect to initial value. So it's quite simple to understand the values like epsilon 1, 1, 2, 2, and 3, 3. So just elongation or compression of the axis of the dimensions. And then if you have, for example, 2, 1 or 1, 2, actually it represents rotation. Because we have delta u2, because for example, you had a square and it was compressed like this, elongated, it's like rhombohedra. So you get elongation here along y, okay, of this dimension. So actually it will describe this dimension, component delta u2, along direction y of initial dimension x1. So it will be your component 2, 1. Okay. And as we work with we'll get very, very small deformations. Actually, this elongation along with respect to the length, it will give you an angle. So it represents like rotation of your axis, this component. So this is deformation. So, and if you have a simple deformation, for example, expansion of your body or compression of your body, so we can describe very similarly just by diagonal. Epsilon 1, 2, and 3, or 1, 1, 2, 2, and 3, 3. Okay. Yeah, and then pure shear, the same as a strain, as a stress, sorry, we describe as with these numbers 1, 2. This is in the plane x and y. Okay, we describe with these components or just x, x, y, y with opposite sign. So this is a shear strain, how we describe. So, and actually of deformation, for example, thermal expansion is a deformation. Okay. Deformation due to the temperature. Okay, we have deformation due to the temperature. So the thermal expansion, this is 0 order tensor. This is the second order tensor. So the thermal expansion is a second order tensor. Okay. So if your system is trigonal, it's uniaxial crystal. I hope you remember my table several slides before. So we have like 2 independent coefficients. So it means you are going to have like 2. Oh, I answered the question. Terrible. Okay, never mind, next. I said the answer. I could take another example why I took a trigonal. Okay, so we have an example of different crystals of different systems, okay, of a thermal expansion. So we see, for example, monoclinic, we have 3 different components, but it should be 4 even, so we didn't measure a 4th one. Orthorhombic 3 coefficients of thermal expansion, hexagonal 2, and you see that it might be very different. What we cannot say from the symmetry, the values of these coefficients. We can say if we are going to be different or the same or 0, but we cannot, or we will have opposite sign, but we cannot say that this material will have a huge thermal expansion or low thermal expansion just from symmetry reason. Okay. So we can say how much not equal members there are, how much independent constants, which are 0 or opposite, but we cannot say the values. So this needs to be measured. Okay. Piezoelectricity. We get to the higher order now, to the order 3. Okay. So Paul already this morning explained what is piezoelectricity. Okay, so if you apply strain, we get electric field, so it will be, sorry, not electric field, polarization. So when we have direct piezoelectric effect, or if we apply a tension or electric field, when we get a deformation. Okay. So piezoelectricity is a third rank tensor because it will describe relationship between stress and polarization. Okay, stress is second order. This is the first order, it's a vector. So piezoelectricity is the third order. Okay. So it means here we have 9 coefficients. Here we have 3 coefficients. So it will be 27 independent coefficients. And so, for example, polarization along direction 1, we can induce with different type of stresses. Okay, so it depends on material and the symmetry and how much coefficients are not. Okay. So all uniaxial stress is easier, so we can, for example, the polarization along direction 1, okay, will be induced by stress, for example, 1, 1. So, and the relationship between this will be described with coefficient 1, 1, 1. Okay, so it's 2, 1, 1 is coming here, and this 1, 1 is coming here. So polarization along direction 2, if we apply this uniaxial stress along x, we can describe with coefficient 2, 1, 1. And polarization along direction 3, with the same stress, it will be described with coefficient 3, 1, 1. Okay. So shear stresses, as I didn't say, but the stresses and stress and strain, they are also symmetric tensors. So it means with respect to diagonal, we have the same coefficients on both sides. Okay. So when we apply the shear stresses, you remember it was 1, 2, and 2, 1. You had 2 components. Okay, so it will be described by this equation. Okay, sigma 1, 2, and 2, 1. So they are equal in between the value. So it will be described by 1, 2, and 1, 2, 1, and so on. And so on. So there are 27 components. Just describe complete relationship between 9 components of stress or strain and the field and polarization, which is a vector. Okay. But as strain and stress, they are symmetric tensor, so it means we have only 6 constants, not 9, which are different. We will need only 18 independent coefficients in general, not 27. So, to simplify, because until I wrote the second order, it was still okay, but even now I'm not trying to write these 27 coefficients. It starts to be big. The people decided to simplify writing, and they proposed matrix notation. Okay. So it means that instead of writing 2 numbers for stress and strain, okay, instead of writing 1, 1, 2, 2, 3, 3, 2, 3, 3, 1, 1, 2, and so on, we replace these 2 numbers, which relates the stress of a strain, with 1 number which goes from 1 to 6, because we have 6 independent constants. Okay? Instead of writing, as I did before, for example, sigma 1, 1, and so on, so we're going to write sigma 1, sigma 2, sigma 3, and then we'll do this. Okay, sigma 4, sigma 5, and sigma 6. Okay, so instead of writing 1, 1, I just write 1. Here 2, 3, but then I have 4, 5, and 6. And then here we just repeat sigma 6 because it's symmetric. This is sigma 5 and sigma 4. Okay. So this is matrix notation. You can recognize it quite quickly if you see 4, 5, or 6. Because in tensor notation, we always have just from 1 to 3 the numbers. Because it relates the coordinates, x, y, and z. And matrix notation is like shortening of writing. And then we get the numbers from 1 to 6. Then, for example, if I write polarization as a function of a stress, then we get piezoelectric constant, just only with 2 coefficients. But A, which relates to the polarization, I, which relates to the polarization, it goes from 1 to 3. And the G, which relates to the stress, it goes from 1 to 6. Okay? Because it's shorter notation. And then all the mathematics can be used as a matrix, as a simple matrix. It's much easier to calculate. And then the general expression of piezoelectric constants becomes this type of matrix. Okay, so we have only 18 members. So usually all the tensors, they are written already in the matrix notation. When you find the values and so on, it's usually in the matrix notation, not in the tensor notation. So it's shorter form, okay? But if you, for some reason, you need to come back to the tensor notation, don't forget to multiply to divide by 2. Yeah, because it's 2, okay? And then for the calculation, so it's quite easy. So in that case, then, for example, stress and strain, we're going to write in this form. Okay, so it's not anymore 3 by 3 matrix. So we have 1 column matrix from 1 to 6. And then we can use mathematics of the matrix, simple one. Okay. So for example, I want to calculate polarization as a function of a stress. So you have a matrix. So P1 is just you multiply the first line with a column. Okay. You find. So it's quite easy to apply, it's just matrix. Okay. And the same. So if you want to calculate now the strain as a function of a field, so you do transpose matrix. Okay, you rotate your piezoelectric constant matrix, and then you have U1, 2, 3, and you multiply, and you get the strain. Okay, so then you actually, for the direct and converse effects, we use the same matrix, we just rotate it, we do transpose, okay? And then you express the polarization as a function of a stress, or the field as a function of the deformation. So remember that the tensor notation, the third order tensor will have 3 coefficients. And if you go to the matrix, it gets to the 2 coefficients. But it doesn't mean that the tensor is order 2, it's order 3. Okay, but one of the coefficients will go from 1 to 6. Yeah. So the rotational matrix on its inversion center is -1, -1, -1. Okay. So if we transform x1, x2, x3, it goes to -x1, -x2, and -x3. So 1 goes to -1, 2 to -2, and 3 to -3. And then, but you would say, okay, but what I do with 4, or 5, or 6? Okay, so we know that we need to be careful, because, for example, if we do, I don't know if you can see this. Can you see the writings? No? I put the white somewhere. Okay. So anyway, 1 goes to -1, 2 to -2, and 3 to -3. Okay. So for example, D11. Actually, what it is, it's D111, because this 1 has 2 members inside. Okay. So we need to think that, okay, the first one I transform as normal 1, but the second number, I need 1 will transform as 1, 1. 2 transform as 2, 2. 3 will transform as 3, 3. 4 will transform as 2, 3. 5 will transform as 1, 3. Sorry, 6 will transform as 1, 2. Okay? So 1, 2 will transform as -1, 2 plus. So it will go to 6. Then 1, 1, it will get to 1. 2, 2 will go to 2. 3, 3 will go to 3. And then, but to 3, it will go to 4. 5. Okay? So it means the first number transform to the -1. And the second will go just to the same. So it means that D11 will go to -D11. D12 will go to -D12. D13 will go to -D13, and so on and so on. And each member will go to its -1. And this makes that's why centrosymmetric materials with piezoelectricity. Okay, it's 0. Okay. So the light is too strong. No. It's okay? Okay. So all the centrosymmetric groups are not piezoelectric. So we know which are centrosymmetric, so we are not piezoelectric. And also the group 432 is not piezoelectric. It doesn't have centrosymmetry, but its symmetry is too high. It cancels. If you apply one constant after another one, finally it will cancel all the constants the same. So you can try at home. If you want to practice 432, to check with piezoelectricity, when you get a bonus tomorrow, who succeeded. Okay, so when, I mean, all with the electric, piezoelectric constants, we are calculated already, so you don't need, to do by yourself and so on. You can find for each symmetry, each point group. So as you see, it's not so easy as in the second order tensors. For example, you have several different tensors of piezoelectricity for hexagonal systems. So it really depends on the point group. Okay? In the second order tensor, I said, oh, it's trigonal, tetragonal, hexagonal. I know how it looks like. Piezoelectric is more complicated. So it really depends on the symmetry, precise symmetry, and you need to find in the tables what is your coefficients which are not 0 and which are negative, I mean, how we are related and how many different coefficients we have.